We can use the t-distribution to compute an array of important statistical tests. The first one is the one-sample t-test. This test compares the mean of a random sample from the normal population with the population mean proposed by the null hypothesis. So t equals x bar minus mu naught divided by s divided by the square root of n. Here, mu naught is the mean value proposed by the null hypothesis. The null hypothesis for a one-sample t-test is the population mean equals mu naught, and the alternative hypothesis is the population mean does not equal mu naught. For our iris sepal width data from the previous video, recall that mu equals 3.43 centimeters, x bar equals 3.94 centimeters, s equals 0.343, and n equals 5. So the null hypothesis for a one-sample t-test would be the sample of sepal widths came from a population with mu 3.43 centimeters. And the alternative hypothesis is that the sample of sepal widths did not come from a population with mu equals 3.43 centimeters. If we calculate the t statistic, it's 3.94 minus 3.43 all over 0.34 divided by the square root of 5. And that gives us 3.32. We can compute the t critical value in R using the qt function. Within the qt function, we need to assign our alpha, which is 0.05, and we divide that by 2 to designate that we're looking at a two-tailed test. And we want to give our degrees of freedom, which is 4. And that gives us a t critical value of 2.78. If that critical value is lower than the t we calculated, that gives us evidence to reject our null hypothesis. If the t critical value is greater than our t statistic, then we fail to reject our null hypothesis. Since our t critical value of 2.78 is lower than our t statistic of 3.32, this indicates that the sample of 5 iris setosa flowers probably have different size sepals than the iris setosa population. In R, we can run the t.test function to verify our results and use that to compute a p-value. And so here we want to make a vector x that has all 5 of our observations. And then in the t.test function, we want to add that vector of observations and our mu, which is 3.43. And we run that. It calculates for us a t statistic of 3.32, a degrees of freedom of 4, and a p-value of 0.02938. It does not provide us a t critical value, but we can use that p-value, which is less than 0.05, to state that we reject the null hypothesis that the sample of sepal widths came from a population with mu equals 3.43 centimeters. There are some important assumptions underlying a one-sample t-test. 1, that the samples are random. 2, that the samples are independent. And 3, the sample values are normally distributed. This last assumption begs the question, how do you know if your values are normally distributed? There are a lot of ways to do this mathematically, which we'll discuss later on this semester, but for now, we just want to use the eyeball test. Simply plot your data using a histogram or density plot and see if the values look normally distributed. If it looks like this, then you're good to go. If it looks like this, it may not be normally distributed. And if they're not normally distributed, there are some solutions to it that we will discuss in a few weeks.